please join me in welcoming Isaac Wren, Higher Dimensional Polygraphs and Operatic Rewriting from ENS, because I'm not going to try and pronounce ENS. Thanks.
Thank you for the introduction. Thank you for the organizers for this opportunity. Today I'll talk to you guys about work that I did for my master's thesis under the supervision of Philippe Malbos at ENS de Lyon, and out of which we have a preprint, which is on the archive. And I'll put the full reference at the end of the presentation. And if it's blurry and things can't be read, then I might try to find a different solution, because right now I'm sharing screens with my iPad via Wi-Fi. So hopefully everything works well. After a brief overview of what I'm going to talk about, I'll talk about shuffle operads, then higher dimensional shuffle operads, and then polygraphic rewriting in shuffle operads. So everything is done over shuffle operads. It's not necessarily the only context for this sort of rewriting theory applies, but it's the context in which I worked on it. And I think it gives a good idea of what we can do. So this work takes place in the context of algebraic rewriting. So what is algebraic rewriting? First, rewriting can be seen as a combinatorial theory of equivalence. This is a notion introduced by, or presented by Newman in 1942. And algebraic rewriting is, the idea being that instead of saying that two objects are equivalent, we say that we can rewrite one into the other. So we orient the relation. And this gives us paths of rewriting steps, for example. Algebraic rewriting is rewriting in the context of algebraic objects, and sometimes we talk about congruence, for example, congruence of integers. And this has various applications in computer algebra to solve problems such as ideal membership, calculating resolutions, or calculating homological properties. On the side of constructive mathematics, this can be used to construct cofibrant replacements, and in particular, small cofibrant replacements. A cofibrant replacement being sort of a free object that is equivalent to the original object. This appears in the context of model structures. Some examples where rewriting and algebraic rewriting have been applied are monoids, algebras, commutative and associative, higher categories, and operads. And this is this last case that we will be looking at today. And our approach is to use higher dimensional categories, which will actually be strict. And we use it mostly from a combinatorial point of view in order to represent our rewriting systems. And so, for example, rewriting steps are morphisms or one cells, and then relations between rewriting steps would be higher dimensional cells. First, the underlying algebraic object, which is shuffle operads. In my abstract, I mentioned symmetric operads, which are the original form of operads. But for rewriting purposes and time constraints, I will only talk about shuffle operads. The general idea is, if associative algebras are linear versions of words, then shuffle operads are linear versions of planar trees. And in fact, if you take a thread-like planar tree, that gives you exactly a word, so an element that could be part of an associative algebra. And so first, an example, which is an example that I'll carry out throughout the presentation, is the shuffle operad Lie flat. So it is generated by one operation mu of arity 2 and satisfies the shuffle Jacobi relation, which is this relation right here. And this is related to a symmetric operad called Lie, and related to Lie algebras. So we can compare with this usual Jacobi relation for Lie algebras, where basically what we did was we replaced this bracket by a mu, a binary operation. And so we have a correspondence between these terms. The order isn't very important. I just want to draw your attention to the fact that these trees are drawn in a very specific manner. This is why we talk about shuffle operats. The smallest the smallest integer that appears on this side must be smaller than the smallest integer appearing on this side. So here we have a 1, and here we have a 2. However, if we look at this term here, the smallest integer on the right is maybe we look at this one. The smallest integer on the right is a 2, and the smallest, the smallest integer on the left is a 2, and the smallest integer on the right is a 1. So 2 is greater than 1. This is not valid in terms of the permutations of 1, 2, 3. And so the reason for these constraints is that we want to avoid having symmetric actions, so we need to encode them explicitly. And I guess this isn't very clear, but there is a formal definition that I will put here, just so that everything is well defined. So shuffle operats were introduced by Dotsenko and Koroshkin in 2010. And they can be seen as internal monoids in a monoidal category. So this category is the category of collections, which is a presheaf category on the category of finite non-empty ordered sets, and with values in vect. And vect is a vector field over some field, a vector space over some field of characteristic 0. This definition is a bit redundant because all we need are these V of k, for k, any ordered set of cardinality k. And we say that V of k has the elements of arity k. The monoidal product in this category is this shuffle composition, circle SHA, which is this rather complicated formula, direct sum of V of k tensored by k copies of W with the right ordered sets. And this second direct sum is indexed by F, which is a shuffle surjection, which means that smallest preimage of 1 is smaller than the smallest preimage of 2, and so on up to k. The unit for this composition is a collection concentrated in arity 1 and of dimension 1. And I guess small k in bold is the field. So this is a monoidal category, and we denote by SHA up, the category of shuffle operats. Now I wanted to introduce be a bit more specific about what I mean by planar trees. And so using this definition, and if we take a collection V and a basis X, so in each arity we choose a basis of V of k, then V circle SHA V has a basis of planar trees of the following form. So X naught corresponds to the left side of this tensor product, while X1 to XK correspond to the right-hand side. And I tried not to go back and forth too much. And in this planar tree, we impose that these top integers, which we call inputs, be in a specific order. So for each of these subtrees, they're in increasing order. And then these first inputs for each of the higher trees are also in increasing order. So this is basically what we've done is we've taken a deck of cards that is sorted, and we've, I guess, shuffled them by taking subsequences in increasing order. Since this tree takes up a lot of space, we also introduce inline notation. X0 bar F, where F is the shuffle surjection associated to this tree, or even X1, XK, or even shorter X1 bar vector XK. We can also iterate this composition. Here we only have 2 layers of trees, but we can add more and more vertices, and these produce tree monomials, which will be a basis of the free shuffle operat on X. And so we can check that this forms an operat. And we refer to the elements of arity k as polynomials. Another notion that is not only for operats, but this is where we'll be working, it's the notion of a context. So using the planar trees, we can define a context of inner arity K as a tree monomial C square bracket, where we have a bunch of tree monomials around a new symbol, box K, of arity K. And the idea is that we can replace this box with any actual tree of arity K. So if we have a polynomial of arity K, C bracket F is a linear combination of C bracket UI, where we just replace the box with UI. This allows us to define, or at least give a definition of bimodules over an operad, which will be used as a sort of application of the rewriting. So a P bimodule is a collection M equipped with linear maps for each context C of inner arity K. And we can see this as the context acting on the collection. And you can think of, for example, a bimodule over an algebra, where the algebra acts on the left and the right, which you can see as a sort of context. So this satisfies the usual associativity and unit relations. So a trivial context acts trivially, and then if we act with one context and then another, it's the same as gluing the two contexts together and then acting on M. So that concludes the algebra part. Next is the category part. And so we'll be working, as announced, with higher dimensional categories, and specifically with strict omega categories. So these are infinity categories where all of the composition, associativity, and identity rules, relations, and axioms are strict. And so here's the definition. A shuffle omega operad is an internal strict omega category in SHA-OP. So this means that each object of n cells is a shuffle operad. And so we have morphisms, which go in both directions, which are morphisms of shuffle operads. It's a bit small, but we have S on top. This is a source morphism, but we have a T on the bottom, which is a target morphism. These give the source and target of n cells. And then we have in the middle, we have an I identity morphism, which associates to each object an identity in one dimension higher up. So if we just restrict it to P0 and P1, this would be a regular category with morphisms and identities. So these satisfy some axioms which I will not detail here. Well, not all of them, including associativity and identity for compositions, as well as globularity, which I'll detail. I forgot to mention that this is something that Eugenia Cheng already talked about. In higher dimensions, there are more compositions. So in dimension 1, we just have composition, we concatenate morphisms. But in dimension 2, there are horizontal and vertical compositions. And in n dimension, there are n compositions. And so these satisfy certain axioms. I just want to say that globularity means that the source of the source is equal to the source of the target, and the target of the source is equal to the target of the target. So if we take an n+2 cell, A, we can draw its source and target as paths or arrows, and then these two arrows share the same source and target. So this creates a sort of bubble or globe. Our goal now is to present in these in omega categories. And so we will be using a structure called either computad or polygraph, introduced by, respectively, by Street and Bironi in the, I have the date somewhere. I guess I don't. 70s or 80s. And so next slide. There are various definitions, and I also don't have the time to give the full definition, so I hope this diagram will give an idea of what is happening. It's rather complicated. So first we can look at the bottom row, where we have x0, x1, xn, and each x is an indexed set. So it's a set where each element has an arity, and xn is the set of generating n cells. And if we look at a generating n+1 cell, it has two morphisms going to the free shuffle operad of n cells, xn sha, which are the source and target. And if you're familiar with cellular complexes or CW complexes, you can think of it when we glue an n+1 cell by specifying its boundary. Here, instead of a boundary, we have a source and target. And then for each of these generating n cells, we have the associated free shuffle operad of n cells. And this top row is exactly the free shuffle omega operad generated by x. So it is by construction a shuffle omega operad. And the shuffle operad presented by x will be the co-equalizer of these two morphisms. And we can see this exactly as saying it is the operad with a certain number of generators satisfying a certain number of relations, where the relations say source equal to target. To come back to our example of Lie-flat, we already gave a presentation by generators and relations, which we can just put in the framework of an omega polygraph. So we have this polygraph X Lie-flat, where we only have 0 and 1 cells and everything above is empty sets. And in fact, we only have one generating 0 cell, mu, of arity 2, and one generating 1 cell, alpha, of arity 3, which I write like this. We take this monomial and we rewrite it into this polynomial. And to give an idea of what the 1 cells in general look like in the free shuffle operad of 1 cells, we look at these two elements. So we have a tree where the vertices are either 0 generators or 1 generators, generating 0 cells and generating 1 cells. And in this top example, we have an alpha here, which will rewrite the top 2 mu's as such. And basically it's rewriting in context. We can also rewrite the bottom 2 mu's because they also match. And so this is 2 ways of rewriting this tree monomial using a rule in context. Or sorry, I guess, yeah, a rewriting rule or generating 1 cell in context. However, polygraphic presentations aren't really enough. They don't give any more information than a presentation by generators and relations. So what we are looking for is some sort of higher dimensional coherence, which comes through the form of polygraphic resolutions. So first, a small definition. 2 n+1 cells are parallel if they have the same source and target, which may or may not be counterintuitive. Then if we take tilde to be the equivalence relation generated by source and target are equivalent for any n+2 cell, we say that xn+2 is acyclic if for any pair of parallel cells we have f tilde g. So the idea is saying that we can somehow pass using, my pen is very big, using various generating n+2 cells to get from f to g. And this is basically saying every path is equal up to maybe homotopy, if you will. And we say that a shuffle omega polygraph is a polygraphic resolution if each index set is acyclic. The interesting part about polygraphic resolutions is that we can construct an exact sequence of p bimodules as follows, where each bimodule is generated by the generating n cells. And the boundary maps are bracket of source minus target, where the bracket is basically some sort of abelianization. It sends contexts, which are normally trees in X, to elements of P, and the various compositions to become addition. For dimension 0, the bracket is a bit different because technical reasons, but I put the details here. And the result that we get is that if X is a polygraphic resolution, then P bracket X is exact. So what this means is if X is acyclic, then P bracket X is acyclic. This result isn't really new. It has already been done for monoids and higher categories, but we just did it in the context of operads. We have a standard polygraphic resolution, just to show that one exists, where the generating 0 cells are a basis of P seen as a collection. Then the generating 1 cells are just saying that shuffle composition are just applying shuffle composition to these formal elements. And then in higher dimensions, we introduce a generating n+1 cell for any pair of parallel paths. So this ensures acyclicity. However, it's very large. And so I'm going to overstep my welcome a bit to explain how we can get a smaller polygraphic resolution using rewriting. So this is where rewriting comes into play. For rewriting, all we need to do is look at the lowest dimensions, because if we make the lowest dimension smaller, then actually everything else becomes smaller as well. So we look at 1 polygraphs, which are just, we can truncate the omega polygraph to 0 and 1. We take X to be a left monomial 1 polygraph. So every source of a generating 1 cell is a monomial. A rewriting step is a 1 cell, which rewrites lambda C bracket U plus V to lambda C bracket A plus V. So the U becomes an A, where U and A are the source and target of some generating 1 cell. And there's a technical detail here where C bracket U cannot appear in the decomposition of B into elements of the basis, because otherwise we would get infinite rewriting steps. We could rewrite the B using the same rule to infinity. So this motivates the following definitions. A rewriting path is a sequence of rewriting steps, and a 1 polygraph X is terminating if there are no infinite rewriting paths. The next notion of rewriting is a branching, which is a pair of rewriting paths with the same source. Recall that my example had 2 rewriting paths with the same source. And they were actually local branchings because both paths were rewriting steps. And we can classify these. If the 2 cells, F and G, rewrite on different monomials of the source, then we get an additive branching. If they rewrite on the same source but do not interfere with each other, it's multiplicative. If they do interfere with each other, we say it's intersecting. And if they interfere with each other and there's no extra context around, like here and here, then we say that it's critical. The important notion that comes out of this is confluence. The 1 polygraph is confluent if every branching can be extended by rewriting paths that converge. I guess that have a confluence. And the 1 polygraph X is convergent if it is confluent and terminating. And the reason that we are interested in particular in critical branchings is for the critical branchings theorem. We have a coherent version because it's a cell here. If we take X to be a terminating 1 polygraph and we add a generating 2 cell for each critical branching, so we assume that there exist converging paths, and we add a 2 cell, then we get an acyclic index set of generating 2 cells. So this is much smaller than for the standard polygraphic resolution. If we go back to the example of X lead flat, we get this sort of large diagram where these 2 rules are this is very small, but these 2 rules are the ones that I gave before, and we can actually extend these to the same ending point. And so we only need to add 1 cell to get an acyclic index set of generating 2 cells. And the idea is to then continue this procedure in higher dimensions. And so this is what we did in our preprint. We defined an overlapping polygraphic resolution where we start with 0 cells and 1 cells of a convergent 1 polygraph. And then we extend these to an overlapping polygraphic resolution where the the generating n cells are overlappings of n generating 1 cells. So if we only have one cell, it's just by itself. If we have 2, then we get a critical branching. For 3, it gets more complicated, and this is where operads show more complexity than algebras, because for algebras we would only have something like this, while for operades we have much more, and so on. And so the result is that this is indeed acyclic, and we can use this to prove some results we couldn't do with a standard polygraphic resolution. So I would end with this homological algebra result, where an operad P with a convergent quadratic polygraphic presentation is closed. So quadratic means that the generating one cells have source and target of size 2. There are only 2 inner vertices. For example, Li has this. And Kosul is a certain homological property which says that we have a way to calculate a minimal model. And so the idea is to take this convergent presentation, which is we take the one polygraph, extend it to this polygraphic resolution of overlappings, study the P bimodule resolution, which I've constructed, whose generators are concentrated on the superdiagonal, so n plus 1. We can then calculate the Quillen homology from this resolution, which is concentrated on the diagonal, and then this is a sufficient condition for Kosulness. I'm going to end now, and if there are questions or maybe in Discord, we can talk about this more. In conclusion, we have a polygraphic resolution of an operad, and we have a way of constructing a relatively small one. One major issue is that in this category of internal omega categories, we didn't find a model structure, but there is a similar category of differential graded operads where there is a model structure. And so one question we have is, can we construct a similar resolution in this category? And in this case, with the analogous construction of overlapping resolutions, give a minimal cofactor replacement. And then the other possibility outlook is looking at other monoidal structures and seeing if we can rewrite in those. So I have listed here shuffled operands. Thank you for listening, and if there are any questions.
Thank you.